Very good.
Well, I also sent you a message of Sambala.
Yeah, I know, to have a meeting of the editors. So we will try to find. No,
During the
Telly,
conference?
yes. So
Okay.
she was proposing lunchtime sometime. So we need to know how many editors will be there. So show you for sure.
Yes, yeah, sure. Yes. I must.
Yeah. So then, Ted, you're not going to be there, right? No. So we will see if maybe Catherine will be there. Yes. So she was proposing lunchtime sometime. So we need to know how many editors will be there. Why am I seeing my voice so delayed? It was the YouTube channel.
YouTube, yeah.
Yeah.
Okay.
So Daniel, we should tell you that Telly will mute and turn everyone's camera off right before we start, so you have to turn yours back on and unmute
Okay,
yourself.
thank you. Yeah, all right. I'll just get my screen sharing ready and I'll make a note to do that.
And you have about 45 minutes talk, and there's a Q&A session for 10-15 minutes.
Sure. I'll keep I'll watch the clock.
Oh, Greta is coming. Hi,
Good
Greta.
morning.
Good
How you doing?
morning.
Morning.
Hey.
I'll tell you, it might be even earlier where you are than where I am.
Yeah, you're there bright and early.
Well, so are you, right? Even more so than I am. So.
It's just a relative measure.
Still early in the morning. Yes.
You're muted, Telly. We can't hear you. I don't know why.
Hear me now?
Oh, yeah.
Barely.
Yes.
I'm gonna admit everyone in, and then feel free to start sharp at the hour if you.
And I'm gonna chair the
Yes.
session, and I will introduce the Daniel. Okay.
So I let people in.
Okay. Hello, everyone. Good morning, good afternoon, and good evening. This is Shu Takagi speaking. Today, we have a special speaker from the Australia, Dr. Daniel Duke. And he's a senior lecturer in the Department of Mechanical and Aerospace Engineering at Monash University, Australia. He holds a Bachelor of Engineering and Aerospace Technology in 2008 and a PhD in Engineering from Monash University 2015. His area of expertise is the fluid mechanics of the aerosol and sprays, with a particular focus on the pressurized metal dose inhalers. In the former role as a postdoc fellow at the Argonne National University, he developed a range of the novel application of the synchrotron X-ray radiation for sprays. His current research interests span both experiment and simulation-based approaches to complex multi-phase, multi-component fluid flow. He's a Fulbright Fellow 2011, a recipient of the Institute for Liquid Atomization and Spray Systems William Marshall Award in 2013 and 16, and an Australian Research Council Discovery Early Career Research Award recipient in 2017. Today, he's gonna talk about the seeing the unseen, X-ray diagnostics for multi-phase flow. So Daniel, please.
Thank you very much. Thank you for the kind introduction. I'll just share my screen. Hopefully you'll now be able to see my screen. And I'm joining you all the way from Melbourne, Australia. Hopefully the internet connection will hold up. I'm sure the hosts will be sure to let me know if there are any dropouts, and I'll repeat anything in case the sound drops out. I'm Dr. Daniel Duke from Monash University in Australia. I'd like to begin my presentation just with some quick acknowledgements. Firstly, acknowledging funding support for a lot of the work that I'm going to show you today. So this presentation is going to be a little bit of a grand tour through some of the work that me and my colleagues and collaborators have done sort of over the last decade or so. And this work has been funded by many different organisations, particularly the Australian Research Council, and computational support from the Australian government and the United States Department of Energy through Argonne National Labs, where I was a postdoc, and also some of our industry partners, KAC and Kendava Drug Delivery, who are currently supporting our medical spray research. Just to introduce you very briefly to some of the students and staff members whose work you'll be seeing today, please don't go away from this talk thinking that everything I'm showing you is mine. It's most certainly not. It's the product of a large team of researchers, of which I'm just one. So here on the screen, my former PhD supervisor, Professor Honorary, who's contributed to this work over many years, my postdoc, Dr. Lingsha Rao, my current PhD students, Sweta and Italo. Here in the middle here are just a few of my many honours and undergraduate students who are working with us. And on the right here, some of our former students who've gone on to bigger and better things since this work started some time ago. So I'd also like to acknowledge many of my external collaborators outside of the university, particularly my colleagues at Argonne National Labs, who you can see here, who without their support, I would not have been able to do the complex synchrotron experiments that I'd like to show you today. And also on the right, my academic colleagues outside Monash, Professor David Schmidt at UMass Amherst and Associate Professor Michaela Battistoni from University of Perugia, who I worked with extensively on our fuel spray research and who I count as great collaborators, mentors and colleagues. So just to orient you very briefly, I am down here in Melbourne, Australia. Our research team comes from all around the world. We've got our colleagues in Chicago, industry partners in the UK and Minnesota, University of Massachusetts, Perugia in Italy, as I've mentioned. So we're really from all over the place. A very brief advertisement. If you're ever in Australia, please do come and visit us down here in Melbourne. It's a very nice place. Monash University is now in the top 50 universities in the world. #1 in Australia in our area of engineering. We're very proud of that, and it's a very nice campus. So if you're ever in Melbourne, please come visit. We'll give you the tour. So let's move on with the presentation now. I'm going to give, like I said, a little bit of a grand tour, an overview of some of the work that we do and the techniques that we use. Firstly, I'll just talk a bit about the limitations of using visible wavelength light. For any of you who are experimentalists who work in multi-phase flows, you'll know all too well that visible light is both our best friend and sometimes our worst enemy. The wavelengths of light that we can work with can make things very difficult for us. And so X-rays are one alternative that we can use. So very, very short wavelengths. And then I'll talk about the synchrotron light source. What is it? It's a very special X-ray light source. What is it and why do we use it? And then most of the rest of the presentation is really going to be case studies and some theory, although I won't delve too much into the mathematics. But some case studies and looking at some different multi-phase flows that we're interested in. As mentioned in the introduction, I have an interest in pressurized metered dose inhalers, basically asthma sprays. And I've also done a lot of work on fuel injection systems. And so many of the examples that I show you will come from those applications. And I'm going to be looking at a range of different techniques. So if I asked you to think about what's the first thing that comes to your mind when you think about X-ray measurements, you're probably thinking about medical X-rays, X-raying bones, for example. That's an absorption X-ray radiograph. That's just one way of using X-rays. There are many ways of using X-rays. I'm going to show you how we can manipulate some of them to get a bit more information than we can using conventional diagnostic techniques. And then in the end, I'll talk a little bit about where the field is headed and what we can use these measurements for going into the future. So firstly, I'd like to just begin with some motivation by showing you some really nice work that is not mine. This is Ziciar's Hayes group, and here from very nice work from some years ago by Gavaisis and Archimanis. This is cavitation occurring inside a fuel injector. So the fluid is moving through the hole here very fast. This is a transparent model of an injector. There's a spray coming out here, and there are vapor bubbles forming inside here. And in this zoom-in image from Gavaisis and Archimanis, you can see these very nice images of these vortices and these gas-liquid interfaces. Now, using transparent models like this really with visible light is the only way to see what's going on inside a flow like that. And if I were building a CFD model and I wanted to validate it, for example, and I wanted to know where the interface is between the liquid and the vapor, it's very difficult to do that using visible light. The light is being refracted through the curved surfaces. It's being scattered by this rough interface. This is moving around in time very quickly. And so these images, it's very hard to get quantitative data out of these images. And when you have a lot of very small bubbles, you just get a black region like this because there's just too much scattering of the light, or the light's refracted or totally internally reflected. So you run into all these limitations. And if you have to make your nozzle transparent, for example, out of glass or out of acrylic or polycarbonate, it limits your maximum working pressure too. And a real fuel injector made of steel could be running at 3,000 atmospheres. So you're not going to get that in a transparent nozzle. So these are beautiful images, but it's very hard to get quantitative data out of them. So when you're looking at internal flows, potentially with X-rays, you can see through solid objects and actually take measurements quantitatively directly without having to go to have those problems. The other issue is the classical problem of multiple scattering. The image on the left here is from Philip Leik at Bosch. This is an image of an 800 bar diesel direct fuel injection spray in an engine. Knowing about fuel air mixing is critical if we want to do any kind of combustion simulation or measurement, for example. But there are so many droplets, such high number density, that even a very powerful laser beam will multiple scatter to the point where the extinction of light is almost 100%. And if I was to pick a point in my spray here and ask, what is the liquid volume fraction or mass fraction in there at some point in time, getting that quantitatively, except in the most dilute regions, is extremely difficult to do. We also just don't know what the droplet composition is. If I had a multi-component flow and there was evaporation of different species at different rates, I can use laser diagnostics in dilute flow fields to measure those properties, but in a very dense spray where you've got multiple scattering, that can be extremely difficult. If I have combustion and there's large temperature gradients, beam steering will bend the light and make things even worse. And often my droplets are below the diffraction limit of my visible wavelength light, which might be, say, 500 nanometers. And so it's very difficult to see anything below the diffraction limit. So here's where X-rays come in. X-rays are not easy to work with, but X-rays can penetrate optically dense sprays. They're insensitive to temperature and pressure. Their intensity of the scattering does in some cases depend on the species that you have. So you can pull out some information about how they scatter, about what scattered the light. And because the wavelength is so short, they retain information about the structure of what scattered them all the way down to the atomic scale. So if you have micron or nanometer sized objects like tiny droplets, in theory, you can recover information about them. And what's really happening is you're getting a photoelectric absorption and then scattering of X-rays, because the X-rays interact with the electrons around in each atom. So what I'm going to talk about now is how do we use X-rays as a diagnostic tool for multi-phase flow? In theory, they're really nice. They can see through opaque objects and we can do all these things with them. But how do we do that practically? Well, firstly, we know X-rays can penetrate through dense media, and this has been done for many decades. For example, using tube X-ray sources to look through fluidized beds. And Professor Heinel actually has done some very nice review papers and overviews looking at the history and applications of X-rays like this. And you can go and read some of these. So a lot of the work up until sort of most of the 20th century work on X-rays really was using medical or tube-based sources, mostly qualitative flow visualizations. The problem with using an X-ray source, for example, like a medical X-ray source, like a cathode tube, is that you get very low flux. Your photon per second is just nowhere near as high as it is with a visible light source. You also have this problem called beam hardening, because X-ray sources generally tend to be polychromatic. So you've got a range of different wavelengths. The more absorbing wavelengths will get absorbed first. And so as your sample gets thicker, you'll shift the wavelength distribution. And if your detector is not sensitive to wavelength, that can distort the measurement that you get. So you have problems when you try and do this with a traditional medical X-ray source. And that's why we're going to use the synchrotron, as I'll show you in a minute. But to understand this a little better, first we need to understand a little bit about what X-rays are and what some of their properties are. So when I talk about X-rays, I'm talking about photons that have wavelengths of sort of typically 10 angstroms down to less than an angstrom. In nanometers, that's, 1 nanometer down to 1/100th of a nanometer or so. We typically represent that in terms of energy. Energies of X-ray photons are typically in kiloelectron volts, whereas visible light photons are in electron volts. So we're at sort of 1,000 times. The classical radius of hydrogen atom, by the way, is about 1/2 an angstrom. So our wavelengths are at the size of atoms. And that means that our scattering interactions will occur with the atom itself rather than with the thing that the atom makes up. So whereas visible wavelength light will, for example, Rayleigh scatter off of a droplet about its wavelength, X-rays will Rayleigh scatter off of an atom about the same size to a first approximation. They refract, but very, very weakly. So whereas the refractive index of a medium invisible light might be somewhere we're in the ballpark of 1, 1.1, 1.2, whatever, the refractive index of X-rays is typically so close to 1 that it's effectively 1. If you are in the contact region, that is, you're measuring very, very close to something, mostly what you see is just photoelectric absorption. The electrons are just absorbing the photons. Once you get further away, you start to get interference patterns forming, and that's where we get our phase contrast and our diffraction effects. You can also get total external reflections possible, and there are techniques like powder diffraction that entirely rely on this. When X-rays scatter off of objects, scatter off of atoms, most of that scattering is elastic scattering. That is, the photon leaves with the same energy that it had when it went in, but in a new direction. But not all of it is elastic. Sometimes you get a recoil electron and the photon gives a little energy away. That's called Compton scattering, and in a lot of applications, we don't have to worry about it, but in fluorescence we do, and that'll come back in later. but generally most of the X-rays are scattered elastically. And there are a lot of measurement techniques that exploit the fact that X-rays will diffract off of atoms because they're about the same size, the wavelength to the size of the atom. And that's where X-ray diffraction, for example, to measure the structure of protein crystals, to study proteins, viruses, DNA, that kind of thing comes from. That's how we know about the double helix structure of DNA. It's all from the diffraction of X-rays. Some of those techniques can actually be useful in sprays, which may surprise you, but I'll show you at the end of this presentation how that's possible. So what we're mostly interested in when we look at X-rays and sprays is the way in which sprays or liquid droplets or bubbles, any multi-phase flow, absorbs the radiation. When you're at very, very low photon energies, you tend to get the Rayleigh and coherent elastic scattering. But once you're in the range of sort of 5 to say 50 kiloelectron volts, as we typically are for most of these measurements, the dominant effect that you get is photoelectric absorption. And photoelectric absorption is, to a first approximation, governed by the Lambert-Beer law, which you would be familiar with if you've ever done an extinction measurement using visible light, for example. And the intensity that you measure, the ratio of that to the intensity of the radiation that goes into your sample, is going to be related to the line of sight integral of the mass, that's m, and mu, that is the absorption coefficient of the material. And that depends on what kind of atoms make it up. Ultimately, what matters is the electron density of the material, because the X-rays interact with the electron cloud. So if you have something heavier, like iron, it's going to have more electrons and you're going to get stronger absorption. So here you can see how this constant mu varies as the energy goes up from left to right. Roughly speaking, this goes up with the 4th power of the atomic number, and it goes down with the cube of the energy. But you can see all these bumps here and wiggles. It's clearly not a nice smooth line. And that's because when you get to a certain energy threshold, you can ionize one of those electrons, like a core shell electron, and then another one's going to drop down to fill its place, and you pass the K edges and the L edges. These characteristic absorption edges are like a fingerprint for this particular atom. And when we do the fluorescence technique, we can use these to identify the species or composition of our fluid that we're looking at. And you get characteristic fluorescent emissions from absorptions at these lines. When you go to really high energies, you get other strange things happening, like pair production and photodisintegration. But really, those are at energies that we're not particularly interested in. And most of what I'm going to show you today is photoelectric absorption, some elastic scattering of the radiation, and some characteristic fluorescence when we pass through these edges here. So I mentioned before that tube-based X-ray sources are somewhat limited in their utility. And for a lot of the measurements we do, we use a synchrotron light source. So I'm going to show you now what the synchrotron light source is and how it works and why it's so useful to us. So a traditional X-ray tube source is poorly collimated. That is, the light tends to spread out in all directions from the tube, and it produces a very low flux. And obviously with the inverse square law, the further you go away, the lower that drops off. So typically when you're doing a measurement with a tube source, you need a long integration time, and it limits your spatial resolution because of the lack of coherence in the beam and the lack of collimation. Modern X-ray tube sources really have gotten much, much better. They are really orders of magnitude better than they were decades ago, but the synchrotron is orders of magnitude above that again. So there's quite a gap. So this picture here shows the first recorded example of synchrotron radiation production. This is called a cyclotron, and it accelerates electrons around in a circular path. So this is a physics experiment here. And in these electron accelerators, the technicians and scientists who were working on this noticed that they kept losing energy unexpectedly in their electron beam. And so a technician stuck a mirror at 45 degrees around the corner, because you don't want to get radiation. They had a look around the corner to see what was going on, and they saw this flash of light and took a picture of it. This is synchrotron radiation. Basically, when you divert the path of an electron, conservation of momentum means that the electron must release a photon. So there's some loss of energy there. And this is the braking radiation or Bremsstrahlung radiation. And you're getting a loss of kinetic energy in that direction that the electron was going. It moves in a new direction. due to the magnetic field imposed, and now you get a photon released. And if you bend an electron on a curved path, you will get a fan of light coming out. And if the electron's moving at near light speed, due to relativistic blue shifting, if I stand still and watch that electron go past, all the photons that come off from that path will be blue shifted up into the X-ray wavelength range to the stationary observer. And that's basically, in very simple terms, what synchrotron radiation is. So synchrotron sources accelerate electrons in a vacuum, just like a cathode ray tube in an old television or computer screen, and they turn that electron beam to make X-rays. And the synchrotron gets its name because the electron beam is pulsed, not continuous. It comes in bursts, and those bursts can be used to do detailed time-resolved scientific measurements. The advantage of this light is if you design your electromagnets well, you can get a very collimated beam with a very, very small source size. So it's like a point source of light, and that point size is extremely small. The flux is extremely high. And by using electromagnets, where you can vary the distance between them or the magnetic field strength, you can actually tune the wavelength of the photons to whatever you want. A typical synchrotron will have pulses about 50 picoseconds or less, and you'll get a pulse every 150 nanoseconds or less. So very high resolution measurements. And the source is sort of on the order of microns or less. So very, very high resolution. This is the synchrotron that I've done most of my work at. The Advanced Photon Source. It was built in 1996. It's one of the largest synchrotrons in the world. It has 70 beam lines. And you can see the ring-shaped building here. The electron beam orbits around a ring on the inner wall here in an evacuated tube. And every time it turns a corner, some radiation is released. And that's one of the ways we produce X-rays. Very quickly, here are some pictures from, these are copyright to the Department of Energy. There are some pictures of parts of the synchrotron, just so you can get an idea of how big it is and what it looks like. There's a big cathode ray tube with a bunch of accelerating electromagnets. We make electrons and we accelerate them to near light speed. And we then put them into a small synchrotron called the booster ring, where we keep on using radio frequency cavities to give them a bit more and a bit more and a bit more and a bit more energy. And we organize them into bunches. And then when those bunches are nice and tight and they've got enough energy, we use a magnet to push them into the main storage ring, which is where we generate our light. In APS, this storage ring is 1,100 meters long in circumference, that is. And a bunch of electrons will go around 271,500 times a second. So basically your clock frequency for doing measurements, your fundamental frequency is 271.5 kilohertz. That gives you an idea of the time resolution. This big device here shown in the picture here, this is called an undulator. There are a series of magnets here, these yellow teeth. The whole thing sits on a gantry, which can be moved open and closed to change the magnetic field strength. The silver pipe through the middle is the vacuum tube where the electrons travel. The teeth here, these magnets, cause the electron beam to wobble up and down, and every time it makes a little bend to change direction, it releases some light. And if the period of those magnets and the speed of the electrons is tuned right, you can produce a very powerful bright beam of X-rays. This is called an insertion device or an undulator source. It's the one that's most commonly used for most synchrotron experiments. The other way you make electrons is, in order to get them to bend in a circle, in order to make X-rays, when you want to bend your electron beam around in a circle, it has to turn a corner. It's not a circle, it's just a many-sided polygon, and every time you bend it, you use a large dipole magnet to bend it. And when you do that, you get some light too. That's called bending magnet radiation. It's more broadband, it's lower flux, but it's what we often use for a lot of our measurements where we want actually the slightly lower photon energies. So this graph here shows you the number of photons per second per millimeter squared per unit bandwidth that you get. It's just like a normalized flux as a function of the photon energy. The red line is a conventional medical X-ray tube, 1 meter away, like the one you find in a hospital. Up here, note that this is on a logarithmic scale. The green line is the bending magnet in the synchrotron. When we bend the beam around the corner, we can take a bit of the fan and use that. The blue line is that undulator, the large gantry of magnets that I showed you. Because of its periodic nature, it produces a oscillating flux profile with energy. And if you filter out one of those wavelengths with some cleverly designed filters or mirrors, and you pick one of these spikes here, you can see you're well up at orders of magnitude above the bending magnet, which is well above what you would get from a regular medical X-ray source. So 10 to the 10 better. And even the best X-ray sources for a regular lab you can buy, it's 10 to the 5 better than those. Okay, so now I've shown you what a synchrotron is and in very simple terms how it works. It makes very collimated, very bright pulses of X-rays, and they're coherent too. So if you know anything about laser radiation, it's a highly coherent light source, remains in phase over a long distance. The first thing that you can do with this is you can take X-ray images. So this is the most intuitive application. And I'll show you just a little bit about what we do with this first. So if I have a sample, an object, and I'd like to know, it could be a spray, an aerosol, fluid through a nozzle where I don't know its morphology, I can have a plane wave of synchrotron radiation approach this sample and it'll interact with the sample. And then some of that radiation will get scattered, elastically scattered, and the scattering will be at tiny, tiny, like microradian angles. And what will happen is the scattered radiation will interfere with the plane wave and you'll get a diffraction pattern, just like with coherent laser imaging. It's a lot like a hologram in that sense. But remember, the wavelength is extremely small. So weak diffraction, wherever you have a sudden density gradient, like at the edge of a bubble or a droplet in your spray or your flow, that diffraction can be allowed to propagate. So if I move my X-ray, my imaging sensor further away from the sample, the interference pattern grows and grows, and it does what we call edge enhancement. We can now see where there are large gradients in density. And the image that you get is then a combination of both absorption in the sample and this diffraction pattern. And usually we use very, very high energy X-rays, so the absorption is weak and it's nearly all diffraction. And the edge enhancement of the fundamental here, and these little wiggles, is strong enough that you can see where droplets and bubbles and things are, for example. And because the X-ray source is pulsed and it goes very fast, if you have a fast enough camera and a scintillator that can respond to the X-rays and produce visible light quickly enough, you can take a picture every time you get a pulse or a few pulses of X-rays and get a very high speed movie. And because that X-ray pulse is very short, it's picoseconds in duration, it's like having a flash lamp or having a pulsed laser with a very, very short pulse width. So you get a freeze frame of your flow very nicely. Here are some images from my former colleagues at APS who do this for a living. So this is some of their images of jets in fuel sprays. And you can see there's the visible light image using an arc lamp, and that's what it looks like in a phase contrast image, and you can see all this internal detail. So it's very nice being able to see the internal detail in these kind of flows. Here's some work on fuel spray jets, again, from Cyril Kruer from Brighton University and colleagues from Fuel, where again, they can show the density difference. You can see hollow regions inside this fuel jet. So you can get morphological information from this. So let me show you how our group uses this. We're interested in medical inhalers, and what we're interested in knowing is what's the structure of the jet that leaves the nozzle in a medical inhaler. If you get an asthma inhaler and cut it open, it looks like this. Got fluid in here, press down on a valve, some of the fluid goes through a little nozzle and makes an aerosol, a spray, which then evaporates to create aerosol droplets that you breathe in. The fluid is highly volatile. It flash evaporates when it comes out of the nozzle hole. There's evaporation going on and turbulent mixing, and you're getting precipitation of some solids here. But because this fluid is a volatile propellant, like a hydrofluorocarbon, it's going to be flash boiling here, and it might even flash boil inside the nozzle. We don't know because it depends on heat transfer. So we want to know what's the quality and the structure of the jet coming out. If I want to simulate it, I need to know if it's a solid jet or if it's a bubbly jet or a corannular flow, what's the structure of it. And this is about 1/3 of a millimeter in diameter or smaller. So, and it tends to be buried inside this large plastic inhaler, which can be difficult to make transparent. So we need to have a look in here and see what's going on. This ultra-fast imaging technique is perfect for this. Here's a phase contrast image zoomed right in on the inside of that nozzle in the inhaler as I press down the valve. These are two different formulations with different, one has alcohol in it as a solvent and the other one doesn't. The little nozzles here and the flow's going where the arrow shows you. And you can see that the structure of these inside is very different, but critically, the fluid boils before it even comes out the hole. And we're already getting atomized liquid leaving the hole. So this tells us a lot about what the fluid is doing inside the nozzle. And it tells us if we want to model this, we've got to model what's going on in here, not just what happens out here. And if I zoom in even further and I use the time resolution of the synchrotron to its full advantage, I can actually start to see little bubbles and droplets. This may be hard for you to see on Zoom, but I can see where some of the large droplets in the spray and the aerosol come from because of pooling of liquid around the exit of the hole here. It builds up and then gets stripped off into these large drops. And all the fine drops are coming from gas-liquid interaction due to shear inside the nozzle itself. So this tells pharmaceutical device manufacturers, for example, an awful lot about how they make these orifices and how the shape and size of them is really critical to the way the device performs. It's not like a fuel injector or a traditional spray jet used in other applications where you have liquid entirely in the jet and then it vaporizes and mixes and atomizes on the outside. This one happens on the inside too. And so we can go and do a whole lot of parametric studies and understand how this behaves. I'm mindful of the time, so I'm going to move on to show you some other things. But if you have any questions about what you've seen, I'll be happy to go back and talk more about it at the end. The next thing I'll show you is radiography. Now, with the synchrotron, because we have time resolution, we can get snapshots of the absorption of radiation very, very quickly. And a classic example of that is shown here by this work by McPhee et al. In Science back in the early 2000s, where they had a fuel jet and they were able to take a freeze frame image on an area detector, a phosphorized area detector, and measure the X-ray transmission using the synchrotron light source. And they could see a shock wave coming off the leading edge of the jet. And you could see that most of the liquid was sort of in this core region here. Normally, you can't see this because it's surrounded by a cloud of droplets. So since then, our resolution has improved considerably, but this is sort of some of the early work in this area. And ultimately, the measurement you get here of transmission can be related to the line of sight density just through Beer's law, if you know mu, which you can easily find. So how do I use this? Well, firstly, I'd like to, again, giving credit where it's due. This is a nice image, not from our group, from Akira Su's group. And here is a cavitating flow through a rectangular slot. And so you can see you've got a jet, a spray on the outside, and you've got cavitation, vaporization of the fluid on the inside. So if you make a nozzle like this with glass windows, you can look in here and see this. It's very nice. It's a beautiful experiment. What if I want to do that in a fuel injector nozzle that's maybe a fraction of maybe a ½ millimeter in diameter, and it's buried inside a steel or inside a metal nozzle tip? It's very hard to get glass on there to see what's going on. And so X-rays can help with that. So one thing, for example, we did was we made a submerged nozzle, ½ millimeter diameter, out of beryllium metal. Now, beryllium is being a very low atomic number metal. It allows X-rays to transmit very easily, but it's opaque to visible lighting. We can withstand very high pressures. So as a surrogate for, say, the steel you would find in a real nozzle, we could use beryllium, which is expensive, but it gives you a very nice result. And you can make a little round channel. And if we do that and we take an X-ray radiograph, we focus our beam to a point, we take a measurement in time, and then we move. And we make a raster scan map by scanning the nozzle up and down through the synchrotron beam, which takes quite a while, a couple of hours to do. But you get a nice measurement here of the quantitative amount of vapor over space. And you can see the leading edge here. Here is that black region. That's the vapor, the cavitation vapor peeling away from the nozzle wall. You're getting some fluid or a re-entrant jet forming here. And you can see it's mixing into the free stream as you go from left to right downstream. So we can see right through all the gas liquid interfaces and quantify the line of sight volume fraction through the nozzle. If I jump back to our beautiful images of the nozzle with the glass windows here, if I want to probe inside there and say, is that liquid or is that gas? It's very hard to tell because you've got this rough interface here. Is it bubbles? Is it just a rough interface with a large pocket of vapor? It's hard to tell. Here we can actually quantitatively say, yes, you know, this is almost entirely vapor in this black region here. And here we have a mixture of liquid and vapor, like a bubbly flow. So I could do this time average with very high spatial resolution, or I can lower my spatial resolution and record over time and actually get time resolution as well. And if I do that, I can actually start doing power spectra. So if I sit at a point and watch all the gas bubbles go past, and I take the Fourier transform, I can build up a spectral map of what's going on inside my nozzle. As I move downstream, it's getting more and more and more unsteady because of turbulent mixing and because of collapse of the cavitation bubbles causing these sharp changes. And I can see how the frequencies are going up as I move downstream. So this is a little tricky to do because we're capturing every pulse of radiation from every bunch of electrons in the storage ring, and they're not all the same. So we have to normalize out the charge variations in the facility. But when we do that, we get this nice spatially and frequency or spectrally resolved profile. And I could then, for example, go and look at that frequency content, compare that to a numerical simulation, a DNS or an LES, and actually test it to see whether it's capturing the spectral content of the flow properly. And if there are any distinct frequency peaks, for example, due to reentrant jet or Kelvin-Helmholtz oscillation or any other limit cycle oscillation of the jet, we'll pick that up very clearly here in the spectral domain. So this is just an example of the power of doing this. The synchrotron allows you to do with very high temporal or spatial resolution, or you can trade off between them. So the next thing I'm going to do is now quickly give you a brief overview of fluorescence spectroscopy. I mentioned in the beginning of my presentation that most of the X-rays, when they interact with a spray or with any kind of fluid flow, most of that radiation is elastically scattered. The energy of the photons doesn't change. However, some of them do change. If the energy of a photon is sufficient to ionize a core shell electron, then doing so will cause a new photon to be emitted when the hole is filled. And that photon will have a characteristic energy given by the difference in the energy of the electron that drops down to fill the gap. So here's our classical drawing of a bromine atom, for example, which is one of the ones we like to use a lot. Incoming photon, ionized core shell electron. Core shell electron is very tightly bound. The binding energy is equivalent to the energy of an X-ray. So you can really only do this with X-ray radiation. Ionization of outer orbitals can happen with much lower, longer wavelength light, but you need an X-ray to ionize a core shell electron. Another one fills the gap, and then the difference in energy then causes the emission of a characteristic K-edge photon. And the energy of that photon is like a fingerprint of the bromine atom. It's always going to have the same energy. There are a couple of different energies that you can get, but it's a characteristic signature. So it's a spectroscopic technique, just like, say, mass spectrometry, but because we're dealing with core shell electrons, there are only two. Everything is just statistically much simpler. You get very, very few emission energies, very few lines, and those lines in the spectra are very strong. So doing fluorescence spectroscopy with the core shell electrons is much easier than doing spectroscopy with the higher orbitals. The other thing is that the core shell electron, to make an analogy, it doesn't really know about the pressure or the temperature of the environment that the atom's in, and it doesn't know about the valence state. It doesn't care if it's part of a molecule or on its own. So the emission energy that you get is mostly independent of temperature, pressure, molecular structure, etc. Not always true, but mostly. And so we can take that in most cases as a given. Now, it turns out that, for example, in medical sprays, one of the drugs that's often used as an anticholinergic is ipratropium bromide. It's got a bromine atom already in it. So we've got a fluorescing tracer that we can use to look in medical sprays and ask the question, where does the drug go? Maybe I don't care where all the other chemicals in the liquid droplets go. How much drug is in my droplets? That's what ultimately matters to the patient and to the device manufacturer. Let's ask that question. So if we take a synchrotron beam and we focus it down and we give enough energy in the beam that it's above the absorption line for bromine's core shell electron, and we measure how much radiation we put in, we pass it through the spray and we measure how much we get out, some of it gets absorbed, and a tiny fraction of that gets absorbed by the bromine, and a fraction of that gets re-emitted as these K electrons, and a tiny fraction of those are emitted towards a detector, depending on its solid angle and distance. If I correct for all of those losses, I can find out how much of this atom or how much of this drug there was in the droplets in the spray over time. And I can then move the spray around and spatially resolve this. Or I can count up the photons in time. I can gate the detector and just count every millisecond or so how many counts I get, and I can get it as a time resolved measurement as well. But the issue is here that we're dealing with much lower count rates because only a fraction of the photons that go in result in a photon that comes out and gets counted. There are a lot of efficiency losses. And so to do this well, you need the synchrotron because you need an enormous amount of incoming beam flux to get a relatively small count out. But the good news is that it's effectively against a zero background level. And so that means that even if you're only getting a couple of photons every millisecond or microsecond, doesn't matter because otherwise normally you're getting zero. So you're getting your signal to noise ratio can still be good with the right detection equipment. So you can then get the mass distribution. Being mindful of the time, I'm going to move fast through this so I can make my final point in the last few minutes that I have before questions. But here's an example of one way that we can use this, for example, in another application. What if I want to look at cavitation again, but in a proper metal nozzle this time and not an expensive beryllium one? For example, I want to look in an aluminium nozzle. Well, I can't do that using absorption because the metal nozzle wall will absorb the radiation. But if I put tracer particles, such as the cerium nanoparticles, into the fluid, a little bit like PIV, I put tracer particles in the fluid, as long as they're small enough that their Stokes number is low and they follow the flow, I can then use the fluorescence signal coming off of those particles to detect where the flow goes. And so we do that here, and here's a typical spectrum that you get. The energy that we put in is up here. Here are those characteristic K edge lines, a nice sharp double peak that you get here from the cerium. You can measure that out and count it, and you can then move things around and see where it goes. And if I sweep across my nozzle, I can see that I'm getting signal that looks something like this. And this tells me again where those particles are, and it tells me something about the liquid vapor distribution. So where is the vapor and where is the liquid, and the nanoparticles are mostly by density weighting going to be in the liquid phase. And I can do this at different positions. Again, going back to the medical spray, if I have different kinds of medical sprays and I put a common drug in them, I can use that fluorescence technique to get a map over time and space of where the drug is. And if I know how much liquid I've got, I can actually ratio them out and measure the concentration of drug in the droplets over time. And what we find is that you get this cone-shaped aerosol coming out of a medical spray, but sometimes some of the droplets don't have as much drug in them as others. And if the ones on the periphery of the cone have more drug in them than the ones in the center, that drug will mostly coat your cheeks and your throat and not be inhaled. And this is why the medical efficacy of those medicines is lower. And it's something then, now we know about it, we can solve it, for example. So this is how we use this in medical sprays, because ultimately we care about where the drug is and not where all the other chemicals in the spray are. And when we do laser sheet imaging, for example, we're seeing the liquid and all the other components, and the drug is might be, hundreds of parts per million or thousands of parts per million. It's making a negligible contribution to a visible light image. In X-ray, we can isolate it using fluorescence. So in the last few minutes that I've got, and I'm aware that I've got a lot of stuff here, I'll just very briefly touch on X-ray scattering. Now, I had put some theory here, but I won't have time to go into the mathematics. This is where we're going to use that elastic scattering of X-rays to our advantage. Remember in the beginning that I said that when you hit an atom with a plane wave of X-ray radiation, it'll form a diffraction pattern. Well, the individual atoms inside, electrons in an atom, will also cause an interference pattern. And because of quantum physics, we know that the position of those electrons in the electron cloud is random with some distribution, depending on what orbital it's in. And so that means you're going to get fuzzy or smooth patterns coming off of individual atoms, in theory, if you had infinite resolution. So it's a little bit like me scattering, because the wavelength is similar to the size of the scattering object, but because the probability distribution of the electrons is not always deterministic, you're going to get a fuzzy pattern. And so you have to account for that in your data. But if you have a model for that, use this intensity pattern to back out what scattered the light and you can back out what scattered the light and where the scattering came from. So you can look at molecular structure. People have done this to look at protein crystals. That's not really what we do, but here's a classical protein crystallography image. This is how we know about the structure of DNA. I don't have crystals. What if I've got a liquid drop? Well, if it's entirely amorphous, instead of little spots, I'm just going to get rings. And if my droplet is bigger than a few hundred nanometers, now suddenly I'm going to get just a blob. And it doesn't work to just take a picture of it anymore. I have to use a very special device to measure it because the angles are becoming tiny. So I'll be happy to go back through this if anyone's interested. But in simple terms, when you have scattering of elastic scattering of X-ray radiation, and your scattering object, like a droplet, is much bigger than the wavelength of the light, which it is for X-rays, you tend to get what we call this Poirot scattering, where it drops off with a certain known rate, and it's governed by a relatively simple equation. And if I know something about my sample, I can figure out the size of the droplets or what they're made of. And so I can do this in sprays, and I can actually measure the Souter mean diameter of a spray inside the core of the spray. And so here, for example, are some measurements across some diesel fuel injection sprays at different positions where I can back out, if I know the density and the surface area per unit volume, what the Souter mean diameter is. And I can test my liquid atomization models in CFD, for example. I can also do the same thing in my medical inhaler, but the problem in the medical inhaler is I actually don't know the composition of the droplets or particles. So if I can measure their size distribution using an independent method like laser diffraction, for example, and I combine that with my elastic scattering and I know the density, I can throw them all together into some equations. And if I know already what the surface area is from, say, laser diffraction in the dilute regions, I can use the X-ray scattering to back out the electron density. The electron density tells me what the composition is because it tells me what the atomic number of the species is. And so, in short, what I can do is measure how quickly certain species evaporate off in the spray and how that influences the shape of the particles that the patient is going to inhale. And here I've got my blue line being a computer prediction. My white dots is my X-ray scattering, and I can actually see that they line up really nicely, which is a very pleasant surprise because we haven't tuned anything. So I'm mindful of the time running out. So what I'd like to do here is just briefly tell you, where's this going and why do we care about it? What's next? Well, in simple terms, synchrotron imaging in sprays and multi-phase flows, it's not cheap and it's not easy. So it's not going to be a workhorse technique that you're going to use, for example, in R&D. However, what it is really good at is validating simulations and models. So if I've got a CFD simulation, for example, of a medical spray, I can extract a bit out of it, compare it to an X-ray measurement, and check that my X-ray measurement is quantitatively correct, apples to apples, in a way that you simply can't do using laser diagnostics. I can actually tell you is the density or the species concentration, etc., quantitatively correct. And I can actually use this to solve problems in modeling and develop better models. The other direction that this is headed is that synchrotrons are getting better and better. The advanced photon source in Chicago that I just showed you is about to shut down. In fact, probably in the next week or two. And in the next year, they're going to completely upgrade the whole storage ring. And it's about to get 500 times brighter and more coherent. It's already orders of magnitude better than most, benchtop X-ray sources you can get. It's about to get 500 times better. That means even better spatial and temporal resolution, but at limited field of view for your wide field imaging. So they're changing the way that the magnets are set up. And so they're going to end up with much higher intensities. And that means that experiments that might currently take us hours to do, scanning back and forth through a sample, for example, to get a time average picture, we can do that in seconds now. And for time resolved measurements, we can go up in our temporal and spatial resolution, and that trade-off that we have to make between time and space is getting less and less restrictive. And so we can start looking, for example, at colloids, particles, three-phase flow problems, things that were never possible before. And that's all stuff that we're probably going to see in the next 5 to 10 years as these new 4th generation light sources come online. It's not something you can do every single day in the lab, but it's a very nice set of tools you can use to test your models and to quantitatively make sure that they are working the way that you think they are. So with that, I'd like to finish. Here are some pictures of my PhD students working all hours of the day and night at the APS. It's always a fun time to go to the synchrotron. It's a lot of hard work, but it's always worth it. So with that, I will finish my presentation. Sorry for going a little over time. I know I went through an awful lot of stuff, so I'd be happy to take any questions that you have. Thank you.
Thank you very much. Thank you. Thank you very much for a very interesting and impressive talk. So let's open the paper for the discussion. Are there any questions or comments, please?
So I have a question for Daniel. This is Ted Heindel from Iowa State University. Daniel, so if you don't have access to synchrotron, are there techniques that you can use that you can get at least close to what you're doing? I mean, your images and data are fantastic and they're very unique. But if I don't have that synchrotron facility, I mean, you have to travel across the world to get to it. What options are there?
Thanks, Ted. So I talked a lot about conventional medical tube X-ray sources, and I hinted that they've gotten a lot better, but that was perhaps a little unfair. There are mid-range X-ray sources that you can buy and put in a lab. For example, liquid metal jet X-ray sources. They're far more powerful than a medical X-ray tube, but not as powerful as a synchrotron. And you can do some beam shaping and collimation with them. So there are, depending on cost, there are laboratory scale X-ray sources now that are becoming available. And there are X-ray compound optics that you can buy that can give you something within a few orders of magnitude of a synchrotron, but on the laboratory scale. So there are more options becoming available now. And for example, with a benchtop, for example, liquid metal electrode X-ray source now, you can do X-ray fluorescence spectroscopy and elastic scattering measurements in the laboratory. It's entirely feasible. And this is being done, for example, in X-ray tomography research, where you need many sources coming from different angles, and you can't afford to have one big machine and you can't turn your sample like a normal CAT scan. So there are a range of options, but at the moment, they're also very expensive. But I expect that these will, as everything does, will come down in price as the technology is refined. They're still a lot cheaper than a synchrotron radiation facility, though. And tube-based sources are getting better and better all the time as well, because we've gotten much better at making collimating optics and quasi-focusing optics for them, so that you can try and capture more of that radiation and get it into a direct beam.
Yep. Yes, Alfred.
I may have just one question. By the way, impressive experiments, and even considering the small resolution that you can really have. I was surprised by, I mean, when you were showing the medical applications in which you have the spray device, and you are actually be able to measure the drug quantity inside each drop. And you said that not all the drops contain the same amount of drug. What do you mean by that? You mean that same size drops do not have the same drug concentration? And if that is so, why is that? I mean, that is due to the strange way or the peculiar way of injection?
Thank you for the question. So just to be in interest of transparency, the measurements that we do aren't able to instantaneously measure the amount of drug in every single drop. What we do is, if I sit the beam at a point and I integrate as the drops go past, because the beam travels through the spray, I may get many droplets passing through the beam at any point, and effectively have to measure the total contribution of all of those droplets. So it's always ensemble averaged along the direction that I'm measuring. But what we can do is, if we move around in space, we find that the lower mass droplets that are ejected on the edge of the spray, that tend to have a higher angle exiting the jet and get entrained into the flow field more readily, these droplets may not have the same number of nanograms per microgram of liquid, same mass concentration as the amount of drug in the larger droplets that tend to be in the core of the spray. And because they're spatially biased, we can see in space that these droplets over here, the ones that end up over here always have less, and the ones that end up over here always have more. And the reason that this happens is mainly because those drug particles, often they agglomerate, because the drug itself tends to be, especially when suspended, can often be somewhat adhesive, a bit sticky. And the drug particles tend to adhere inside the device itself. They'll get stuck to the plastic components inside, or they might even start to partially clog the nozzle. And so you tend to then get some of them left behind. And because the spray makes a 90-degree bend when it comes out, sometimes what you get on the bottom and on the top can be a bit skewed.
Thanks. Yes, now I see it better. Thanks.
Any other questions or comments? I have a question. I have questions. I am very interested in the physics for the medical inhalers. You show that the ethanol changed the flow structure, and what is the physics, and the how can you scale the phenomena? So there is some scaling law using some dimensionless numbers, and if you have some kind of, so for example, a surfactant, do you have the different behavior?
Here we go. Yes. So
that's what, exactly. Yes.
So the reason that you get different scale for your bubbles as you increase the amount of solvent, amount of ethanol in this case, is simply because of the propellant fluid, the carrier fluid, has a is much more volatile. That is, its saturated vapor pressure is much higher than that of the ethanol, and so it boils away first, and so you end up with ethanol enriched film. The more ethanol you have, the more film you have, and therefore the more interfacial area. But the size of the bubbles scales actually with the pressure inside the chamber. And ultimately what is the parameter that's governing the scaling here is the instantaneous pressure. And that pressure is a function of the mixture pressure of two fluids of different volatilities. So it's like chemistry. It's the activity coefficient of the fluids, and the fact that you've got the weird thing is that the propellant, which is like a R134 refrigerant, for example, and ethanol, they don't obey Raoult's law. You get a deviation. It's not, so the pressure changes non-linearly as you change the molar fractions, and that's why so scaling this based on the pressure is difficult because of that non-ideal mixing behavior. It's a chemistry problem, actually.
Okay. How about if you have a small amount of surfactant?
In fact, yes, the surfactant is exactly what the pharmaceutical companies use when they have a problem with this. So if they're having a problem, for example, with not enough flow coming out the nozzle, the flow is too unstable, they will add a small amount of surfactant. In our experiments, we don't have any, but it's very common, for example, to add some polyethylene glycol or some other surfactant in a small quantity into the canister. And many drugs that you buy off the pharmacy shelf will have some surfactant in them, because the drug particles often do agglomerate or flocculate in the can. That's why they tell you to shake it before you use it.
Very interesting. So maybe not only the like vaporization, also some kind of the surface tension effect might be important to have the size of the, very interesting.
Yes, that's right.
Okay. Any other question or comments? No? If not, I would like to close the seminar today. So thank you very much for the very impressive